This talk on rollups and MEV, or rollups are not exciting enough. So I'm going to talk about how the price discovery in the US cattle market, Gödel's incompleteness theorem, extortion, and monarchy are all interrelated, and the conspiracy all goes back into the Ethereum ecosystem and rollups specifically. So let's start with the easy piece, price discovery in the US cattle market. So suppose you're some guy and then you want to buy some cattle, and then you enter this market, people submit their transactions, their market decisions, encoding their preferences to a mechanism privately, and all those agents have interdependent values, right? So for example, you might value this cattle lower if you know the owner of the ranch that produces this cattle are also at the same time running 10 other ranches that does roughly about the exact same thing, and then maybe the ranch owner's name is Ian, and you don't like that, but anyway. So if you learn that, so it's kind of like multiple people are transacting in a market where each person has a blindfold with private information that are only, testing knowledge that they themselves know. And so then suppose that after a time period, the mechanism computes optimal preference allocation, state change, and allocates cattle to people. And then at this time, the information is made public. There is a public information review period shortly after every agent, every transaction user receives their transaction receipt. Right. So then, since we know that those users have interdependent values, then every time after a public information review, they will converge. Their view of utility will converge to a single view, and thus it creates a lot of, let's say, arbitrage or like liquidation opportunities for them. So then, if we actually draw a graph of the MEV within a cattle market with respect to time, you will see that there is a strong shocks, demand shock for MEV at the beginning, which is mapped in orange, the burst of public info or permissionless MEV. And then after that, suppose the mechanism takes in order flows from new transaction users, and then every time, since we know that order flow comes roughly like randomly, and then every time we receive an order flow, it adds kind of like a super linear growth into the already existing profit that we can get from the existing order flows, right? This is intuitive as you literally have much more action space by having more order flow. You are able to do more ordering optimization. So that's what an MEVT graph would look like. So then let's now go into some more justifications about why this actually applies to rollups and Ethereum ecosystem that we are seeing now. So suppose you're living in a world, you have a lot of DEXs, that's where most of the MEV profit come from. And then if you take like the derivative of the previous graph, you will get roughly those two sides. First you have the orange side and the green side. Green side is the super linear growth coming from randomly incoming order flows, and then the orange side is the burst of MEV. And long story short, if we take some data from the Federal Reserve, which studied the duration of the orange part, i.e. the burst of MEV, every time after a public information review, which is the price discovery, then you can see that the burst roughly lasts 100 milliseconds in Forex markets. So if crypto is anything like that, it should also be in the scale of 100 milliseconds. And then what about the green part, the green growth? If we actually take the all of the blocks that has arbitrage MEV and then order them by the number of transactions within them, and then the y-axis to be the average arbitrage profit, we can see that the arbitrage profit grows more than what we have, have a super linear relation with the number of transactions. And then after some refinement, by kicking out the data that includes NFT launches or net profits, we finally get this, which clearly shows that it resembles the green part in the curve. Yeah, so now with our justification, we discuss how this is relevant to to MEV, to rollups. So we argue that using this abstraction, it helps us to take the upper bound and lower bound on determining the allocation duration, which is the time that the auction should run. So relating to Mahimina's talk just now, this should be the quote-unquote fair granularity duration, where within each batch the ordering is decided by an auction. So let's suppose we have some fast finality time, some price impact duration to be Ti, and minimum allocation time to be Ta. Then we argue that the allocation time should be greater than the price impact duration and smaller than the fast finality time. Whereas, remember that on a rollup, there isn't the notion of block time, so the real block time is actually the time that it takes for the rollup sequencer to do a public information review, which is the time that it takes for the sequencer to make the sequencing data available on some data availability layer. So, yeah. So then, after we have this abstraction, we now think, why is this inequality true? So then, what really is MEV is that it is an allocation of a resource where the resource is what specification should the next state satisfy, i.e., what should be the property that the next state that the next state satisfy. So if we actually map, suppose every agent has a utility attached to a specification, and then we map the specification onto a lattice where the relationship is defined by semantic entailment, as we see here, then we see that the MEV within the supply burst, which is Ti, there are many incompatible demands for MEV, i.e. incompatible specifications on state requirements. And every time after the burst, then it's a long-term slowly but surely superlinear accumulation of order flow. So then to maximize the welfare, which the welfare is also parameterized by the latency, as you have less utility if your transaction is included later. So then given this burst of intratemporal incompatibility and then intertemporal compatibility, then we need that the allocation duration to be greater or at least greater than the price impact duration, which should be 300 milliseconds. And then we kind of also want to bound the fast finality time to make the agents or make the users to wait less, right? They want to get included faster. So then on rollups, that requirement is roughly 1 second. So the takeaway here is that the fairness granularity should be greater than 300 milliseconds and less than 1 second if you really want agent to have a very fast receipt for their transactions. Yeah, so the specific way to implement this is to have the discrete time. So similar to how frequent batch auctions work. And then, so to now we have discussed one of the unique properties that rollups has that is relevant to MEV, which is the high throughput and absence of the idea of a block time. And we see that using the abstraction of price discovery, we see that how we can settle the granularity of the short allocation time. So next, we see another unique property that the rollups has, which is the increased sharing of a single domain for a separation of roles, because rollups, they themselves is a kind of like a specialization of labor, right? Each rollup offloads some tasks to another layer, and so it's like a specialization of labor where each within each society, which is the mega domain, each domain becomes more focused on one thing. So then, of course, if you have a specialization of labor, then you need some coordinator to coordinate different specialists. So then how much MEV will leak from the actual specialist domains, i.e. the rollups, to the shared layers? So for example, we all have heard this modular blockchain meme that people have been sharing. So then, here we try to answer. We suppose that we have 99% of activity on layer 2, and then how much MEV would layer 1, which is the shared settlement layer, or any other shared layer still have? How much do they have? Do they have 1% or something more than that, something far less? Yeah. So here we first partially answer by saying that by devising a shared layer for different rollups, we only partially solve the problem. Namely, we only take back the utility that was surrendered to the malloc by the uncoordination between those rollups, and then give it to MEV. So to see this is that suppose you want to do some cross-chain swaps, then traditionally you can do this easily. So now you devise some market maker bridges, which allows fast latency, and it actually works pretty well. But then what's the business model for bridges is literally like being a better market maker and extract MEV over there. So then that is one very realistic example of how MEV can leak into the shared layer between rollups. So even though with 99% of activity on the two domains, which are rollups, you still leak much more than 1% of MEV onto the shared layer. Of course, a side note is that the malloc that you previously surrendered to need not to be a total chaos. It can be just a bad coordination mechanism. So for example, you have a mechanism M prime allocating a resource A, but then you are using M prime to approximate M, which allocates resource B. So then, first of all, you bring a cost of approximation that you induce in the process of using M prime. And then the second thing is that by using M instead of M prime, you have achieved a greater amount of welfare that you couldn't have achieved using the approximation. So relating to Tarun's talk, actually his talk way back before, we know that there has been some price of anarchy within selfish routing. So this would correspond to the case that a coordinator routing the DEX trades in such a way such that they all get better execution than if they submit it to a fair ordering sequencer. Yeah, so to put this nicely, I suppose many of you have played the game of Sekiro. Here you can see that. And within that game, there's this boss called Guardian Ape, where you cut his head, it still moves like a zombie and fights you. So the head that you cut off is called malloc, and then the actual Guardian Ape is MEV. You can slay the malloc, but the malloc's curse lives on. And then actually Virgil Griffiths, the person who wrote Ethereum is a game-changing technology, literally, he didn't consider this, and thus he didn't consider MEV at all, right? So MEV will take back the part that you have eliminated through slaying malloc. Even more suspenseful music playing. You see that usually in different domains on rollups, you have DEX routing, you have cross-chain swaps, you have liquidity fragmentation. Those are all problems where there are uncaptured, quote-unquote, MEV that were surrendered to malloc, or you could say that the MEV was captured by the malloc. But then you can solve them. But then, for example, using cross-chain market maker bridges, and then he comes in and he makes the malloc look like a rabbit besides him. Yeah. So then we can call this. This is where the incompleteness theorem shows the relevance here. So the worst case MEV that we should have here is that the user should be indifferent between paying their taxes to the malloc or to the MEV, assuming that the MEV profits are centralized and non-distributive. So then, in the worst case, we have that the shared layers having MEV equaling to the total amount of inefficiencies caused by the uncoordination between specialized labors, which is exactly the price of anarchy compared with the original uncoordinated coordination between domains, which could be just they use some very crude cross-domain communication messaging mechanism, which should be logged. So to concretely see this, we first assume that there exists a shared layer for cross-domain coordination where the cost of using it is very small. Then, since this coordination mechanism is a state transition mechanism, then we can encode all of the other domains that we were trying to originally coordinate onto this shared layer domain altogether. And then by the definition that the cost of using it is small, then we have MEV is smaller than epsilon for all layers, for all domains. But then, of course, this contradicts with our observed reality. And for those of you who read the revelation principle in mechanism design, you will notice there is a similarity between here, right? So over there, you're making a mechanism incentive compatible by simulating other domains, and here you are making some mechanism have no MEV but simulating that domain. Yeah, so a concrete example of this paradox of low-cost coordination layer is that when agents collude, they are indifferent between using the current domain or use another domain, since they pay exactly the same. So when one agent is a beneficiary of the current domain, then that agent has the incentive to only use the current domain as a collusion mechanism because it internalizes the revenue for that agent. Okay, so then all in all, our answer to this 99% activity answer should be that the shared layers, including the layer 1, which the rollups offload settlement to, should have MEV equaling to the total amount of inefficiencies, which is the price of energy compared with the original. If the shared layer didn't exist, that is like the equilibrium state you took, and which in turn equals to the amount that Moloch took. But then, you might ask, how those shared layers, including layer 1, how they extract? Like, do they all just be market makers? The market, for example, in cross-chain swaps, you're literally a market maker for market orders, which makes sense. But then for some shared layer that provides data availability or provides settlement, provides security, do they market make an abstract notion of data availability, or market make an abstract notion of security market? Is that how? Yes, sure. That is actually a very good, useful notion. But here we are gonna take a detour and talk about how you can actually have this by extortion. The way is that every coordination layer that's that's cross-domain can just use tattoos, because tattoo is a good way to signal credible extortion, and by saying that, oh, I have the ability to enforce my extortion. So all of the big market makers just have to tattoo like this. This guy in the sauna say that, give me your MEV or I will see you at sauna. And interestingly, searchers actually do go to sauna, a lot of them. So this is, maybe this has already been happening. I would not name who, but you can see, there's a Discord message from an actual searcher who, might be doing this. Yeah, but then jokes aside, we should see that we argue that there is a huge incentive for agents to extort, and there is a huge incentive for agents to centralize, which is to vertically integrate. This centralization could be cross-time, cross-domain. And then thirdly, the extortion can be made credible via centralization of coordinators, where the coordinator is defined to be whoever executes the mechanism in the shared layer that rollups offload tasks to. So for example, it could be the coordinator of the ordering mechanism for cross-domain execution, the settlement layer, security, the liquidity, messaging, yeah. And then thus, we see that extortion can and will happen through decentralization. Of course, we have, I have some anecdotal evidences for this existing, so I'm mildly worrisome. Yeah, so this is where it relates to PBS. If we map all of the sequencing mechanism design onto a 2D plane, we will see it would look like this. PBS has intertemporal decentralization, so that by its nature, if we aggregate builder by the weight of its building power, we will see that if that weight across time is more centralized, then we can say that the coordinators can make a credible extortion. And then secondly, they have a great incentive to do so, because recall from the previous superlinear growth from order flow-based MEV, we see that as the number of transactions in a block size increase, we have the number of MEV growth very fast. And you can actually check out this data is from Unbounded Network, and the analysis is done by Mipasa. Yeah, so the answer to this, a more refined answer after talking about extortion, we can say that yes, the shared layers will have much more than 1% of MEV, despite 99% of activities on layer 2s. So two cases. First is that the rollups can extort other domains, because rollups naturally have a very small permissioned, right now it's all permission sequencer set, which means it's super centralized. And secondly, the other shared layers could extort rollups. This is a Euro case of how the layer 1 makes layer 2 pay for settlement fees, to pay more settlement fees. And then the second one, we further argue that you might ask, if I do extortion, then that's bad for social norms. People will say something bad. Then we argue that the extortion can be done implicitly using something akin to preference curves, where each agent encodes their preference prior to sending to the mechanism into the transaction, and then send the curve together with the transaction to the mechanism. So the curves are basically changing, in this way, are basically changing the focal point of inclusion and the way of inclusion, i.e. the ordering, thus making the extortion implicit and easier for the centralized coordinator to do. So a bit explanation on here is that you have state, you have time, and then you have an abstract blockchain time, where the MEV is the plane intersecting in this 3D dimension. Yeah, and then here comes the monarchy. When you have too much extortion, then what's the end game? What's the end game when we have all those cross-domain MEV existing? We argue that the end game is monarchy. The end game of extortion is no extortion. So traditionally, why people have been advocating monarchy is that the king always wins, so that the king has no incentive to do anything malicious, right? Because if he did something malicious, then he's gonna, get the same result, get the same payoff anyway. So monarchy in crypto traditionally has been used to make systems incentive compatible, because, so for example, the coordinator in ETH POW, which is the miners, they have the ultimate power of deciding the ordering. So they are kind of in a position of monarchy, and then you are recognizing their monarchy by saying that if we give them all of their profits that they could have got if they were a sophisticated MEV searcher, then they wouldn't deviate, and thus they can just do an easy job. So this is the argument saying that monarchy makes crypto more scalable and more secure, in the sense that it has everybody has lower barrier to become king, which and this scalability and incentive compatibility generates huge upside, especially in the longer term, despite you are monarchizing someone. But so now what? Should we just monarchize the coalition of the coordinators? This doesn't sound right? Because reorg is obviously a bad thing that we should prevent, and reorg is essentially a cross-time coalition formed by the coordinators to do extortion, except some of the coordinators are, the time can flow backwards. So what's the path forward? We say that the monarchy profit actually depends on the market structure. We can do several things to change this. First of all, the king receives a tribute equaling to the price of energy that it could eliminate, which is the surplus it brings to the coalition of all of the users in the market, plus any permissionless MEV, because users compete, and thus the profit will, in the end, be computed to be given to the monarchy. So, yeah, and this and then the price of anarchy is defined as where the original equilibrium is the case where everybody operates under a dummy specification on state allocator. So for example, a fair ordering solution, a PGA game, things like that. And then what a better way is to focus on order flow. So for example, you separate the convex and concave advantages from those aristocrats. And this allows us to build market structures in a way such that convex advantages are given to the power of the people and the rest are commoditized. So for example, you can union the demand. So in this case, you create a union of the order flow, and this allows you to commoditize the supply, which is the service that the block builders are providing, or like the validators are providing, or like the other share layers that are providing. The major takeaway on a social level is to say that crypto is the same as politics and government. We make the demands sovereign using similar ways that we make the individuals sovereign. Yeah, so now we have covered the unique properties of rollups, starting from price discovery to incompleteness, which leads to extortion, which finally leads us to discuss monarchy. We've completed this cycle of crazy conspiracy theories that I bet you didn't see this before. Yeah, so some references, you can see our model, the data that we use, and we have incoming mega posts of anthology of ideas on and around MEV. You can see the index here, stay tuned, and yeah, welcome to talk to me about all those relevant ideas on my Twitter.
Yeah, I think that concludes the agenda for today. Thanks for coming. The idea for today was really to sort of expose smart people, hopefully smart people, to the tough problems that are out there in MEV. As you can see, there are a lot of open problems, and we could, like, the people working on MEV research can use all the help they can get. So get contributing. ETH research posts out there. The MEV Boost GitHub is out there. Flashbots launched a website today, so go have a look. And get cracking. These problems are hard, and test yourself and contribute to, like, the future of blockchain. Thanks for coming.